Thank you for joining me once again. This is Dr. Zulfikar Kassam. So we'll continue on with a series of lectures. I know it's been a while since I posted my last lecture, so my apologies, been very busy. But I'm glad to be once again posting another lecture. Thank you so much for your feedback, and I've been getting some emails for requests for information about this course, so that really kind of energizes me. So thank you, keep on the request, and I'm happy to share these slides with you. So if you need to, you can email me on the email that's there on my YouTube channel. And if you need the slides, let me know. I can share the slides with you. All right, so let's move on then. We are now on to lecture 21 of data communications and networks. So in terms of signals and communication, we need to understand that a single frequency sine wave, well, it's very simple. It's not quite useful in data communications. It only gives us very limited information. And in terms of data communications, things are a lot more complicated than a single frequency sine wave. Most data communication actually happen to send composite signals, which comprises of multiple sine waves. And I'll show you an example in a short moment. So a composite signal is made up of many simple sine waves. Now, according to Fourier analysis, now you don't need to know too much. The Fourier analysis is very complicated. Even when I learned at the University of Toronto, Fourier analysis, that was very complicated to understand all the implications of that. But for now, for our understanding purposes, we just need to understand that this Fourier analysis, a very smart scientist, basically managed to figure out how to analyze things, right? So according to Fourier analysis, any composite signal is a combination of simple sine waves with different frequencies, amplitudes, and phases. Right? So any composite signal can be broken down into those three aspects of frequency, amplitude, and phases. So let's do a simple example. If the composite signal is periodic, which is not usual, mind you, but let's do a simple example so we understand the concepts. If the composite signal is periodic in nature, the decomposition gives a series of signals with discrete frequencies. So the important understanding here is the signal has to be periodic in nature. So even if it's composite, if it's periodic in nature, we may be able to break it or decompose that into a series of signals with discrete frequencies. On the other hand, if the composite signal is non-periodic, the decomposition gives a combination of sine waves with continuous frequencies. So we'll see examples of both of these in a short moment. Okay, so let's look at the first examples first. Okay. This is an example of a composite signal, but it has distinct frequencies embedded in here. So this figure shows a periodic composite signal. So this is periodic in nature. So that's the important thing, signal with frequency f. This is an example of 3 alarm systems, each with a different frequency. The analysis of the signal can give us a good understanding of how to decompose signals. So you see this signal, which is drawn here as a function of time. So let's now try to decompose the system into its individual sine waves and see what that looks like. So here we go. So the signal that you saw in the previous slide, when you break it down, actually, it comprises of 3 sine waves. One with frequency f that you see here in pink, right? That's frequency f. Then you have another sine wave, which is frequency 3 times f that you see over here. Okay, so basically 3 waves at the same time, or 3 times the number of periods within the same amount of time that the first one finishes. It's one simple sine wave. And then we have a third wave, which has a frequency of 9 times the frequency of the first wave. So now that we draw these things in here, this is what the previous composite signal had, but it is showing us the aggregation of all these 3 signals. Now, while this is useful information, having the amplitude as a function of time, even more useful or even more compact is the frequency domain plot, right? Which in this case, it's basically a plot of amplitude versus frequency. This is the frequency domain plot. And this is, mind you, a lot more useful because now we can designate these signals into simple frequency values, right? So we have a frequency f, we have 3 times frequency f, we have 9 times f, and the amplitude is basically the height of these lines. So this is very simple to analyze and understand. The reason we are trying to do this is because this is a very simple example of a periodic wave. If you look at a non-periodic wave, it becomes a lot more complicated. For example, our voices, right? Our voices have a range of signals, which is way more complicated than these 3 sine waves that you are seeing here. So let's have a look of what that may look like. This could be, for example, our voices, right? Changing amplitude as a function of time. So you can see a lot of jargon in here, right? However, in the time domain, this looks pretty much very difficult to analyze and understand. On the other hand, if we look at the frequency domain, you can see that our voices could be characterized with this plot, which plots amplitude versus frequency. So this is the frequency domain plot. So you can see here, now we can actually have a feeling and understanding what this looks like. And the reason this is important, for example, is that if you look at our telephone conversations happen up to 4 kilohertz, right? The frequency of a telephone conversation goes up to 4 kilohertz. Now, mind you, we may speak, some of our tones may be higher than that, but that gets cut off. And that's the reason why we may sound a little bit different on the phone compared to real voice, right? We may sound slightly different because some of the frequencies have been cut off. Right? But typically this is what it may look like, right? So basically the amplitude is low over here on low frequencies, and the same thing is for higher frequencies. And then we have this here where our voices mostly range in this frequency range. So this figure shows the non-periodic composite signal, which is, like, as I mentioned, like our voice. It can be a signal created by a microphone or a telephone set when a word or two is pronounced. So in this case, the composite signal cannot be periodic because this implies that we are repeating the same word or words with exactly the same tone, which doesn't happen, right? So it's all over the map. But when we look at the frequency domain plot, it makes a lot more sense. Now, in signals, we try to understand things more in the frequency domain because that's a lot more useful because we're normally dealing with non-periodic composite signals. So how can we make use of this, right? So one of the definitions we come up with in communication is bandwidth, right? The bandwidth of a composite signal is the difference between the highest and the lowest frequency contained in the signal. So the bandwidth, which is represented by the letter B, is equal to the highest frequency minus the lowest frequency. Pretty simple example, right? This is the bandwidth. So this is the amount of bandwidth you will need to carry that signal. So for example, as I mentioned in the voice, we had our bandwidth was the highest frequency was 4 kilohertz in the last example, and the lowest was 0. So as long as we have that bandwidth available of 4 kilohertz, our voice can be carried over. And this will, you'll see this how great this implication is later on. Okay. So now let's look at another signal. This signal here comprises of amplitude versus frequency. So these are distinct signals of different frequencies and different amplitudes. So if you look at this signal and you draw this as a function of frequency, so in the frequency domain, the same signal that you see here or a series of signals that you see here, if you look this or plot this in the frequency domain, this is what it will look like. And the bandwidth is simply the highest frequency, which was 5,000 hertz, minus the lowest frequency, which is 1,000 hertz. So which is equal to 4,000. That's the bandwidth. The bandwidth is the difference between the highest frequency and the lowest frequency. All right, pretty simple definition of bandwidth. So let's do an example in here. We have a series of signal which have been drawn here in the kind of the frequency domain. You can see them, right? Very distinct, right? So as opposed to that kind of composite plot that you saw previously, this is very distinct frequency. Nevertheless, the bandwidth definition is still the same. It's the highest frequency, highest frequency, which is 900, as you can see here. The lowest frequency is 100, so the bandwidth is 800. So in this example, if the periodic signal is decomposed into 5 sine waves with frequencies 100, 300, and so on, all the way to 900, what is the bandwidth? If you draw the spectrum, assuming all components have a maximum amplitude of 10 volts, which is seen in here, you can see the solution is pretty simple. The highest frequency minus the lowest frequency. The highest frequency is 900, as you can see here. And the lowest frequency is 100, as you can see here. So the bandwidth simply is 800 hertz. Okay, very, very simple example. Now let's do another example. A periodic signal has a bandwidth of 20 hertz. So now this time we are given the bandwidth, 20 hertz. The maximum or the highest frequency is 60 hertz. What is the lowest frequency? Right? So the highest frequency has been given to us. So, and we have highest frequency, we have the bandwidth information. We are supposed to calculate the lowest frequency. So in this particular case, we know that the bandwidth is 20, which is equal to the highest frequency, which is 60, minus the lowest frequency. This implies if we take 60 to the other side, or we can do it the other way around, we can bring the 20 over here, bring the frequency over there. The lowest frequency is equal to 60 minus 20, which is equal to 40 hertz. So this will be the lowest frequency. So pretty simple examples, but they illustrate the point in here. So this is the how you would kind of draw it out, if you like, in this example that we just saw a moment ago. Okay, let's do one more example in here. A non-periodic composite signal has a bandwidth of 200 kilohertz with a middle frequency of 140 kilohertz and a peak amplitude of 20 volts. The two extreme frequencies have an amplitude of 0. So draw the frequency domain of the signal. So now we need to understand in here that the lowest frequency must be 40 and the highest must be 240 if the middle is 140, right? And the total bandwidth is 200, so it has 100 on either side. So if we draw this diagram here, this is what it will look like, right? So the bandwidth is highest frequency 240 minus 40, so the bandwidth is 200, right? And it has 100 on each side, and it looks like this, right? So pretty simple example. All right. So why is the bandwidth significant? The important thing for us to understand is the bandwidth is what affects the data transmission rate. The bandwidth directly influences the rate at which data can be transmitted over a communication channel. Basically, a higher bandwidth channel allows for the transmission of more data in the given amount of time, leading to faster communication speed. So what you want to do, obviously, is to increase the bandwidth as much as possible to allow more data to be transferred over that communication channel. Quality of service in applications such as streaming video and voice calls and online gaming, sufficient bandwidth is essential to maintain a high quality user experience. Insufficient bandwidth can result in buffering. You can see sometimes your YouTube video or something like that, anything that you may be streaming slows down if it is waiting to buffer that information. You can also get drop calls if you're in a Teams call or a Zoom call. For example, you can get drop calls if you don't have enough bandwidth or lag, and degrading of quality of service. So that's why you will see that many companies will insist on a quality of service for voice calls, very important, or video streaming, because that ensures that there's a continuous bandwidth available for sending data. Right? And capacity planning is important to understand what are the bandwidth requirements and how do they vary depending on factors such as the number of users, the type of data being transmitted, and the application demands. Understanding these bandwidth needs is crucial for capacity planning to ensure that network infrastructure can support current and future communication demands. The other thing is signal fidelity. Fidelity refers to the accuracy with which a transmitted or reproduced signal represents the original input signal. For example, my voice that will be streamed to you using YouTube, for example. How accurate is that will also depend on fidelity of the signal. So bandwidth affects the fidelity of the transmitted signal. In analog communications systems, limited bandwidth can result in signal distortion and loss of information. In digital communication, on the other hand, adequate bandwidth is necessary to accurately represent digital signals without data loss or corruption. Right? So as long as you have enough bandwidth, you'll be able to stream this information. Otherwise, your computer may be buffering this information for a while before it plays that. Right? So that's where bandwidth becomes extremely important. In terms of efficiency and resource utilization, efficient utilization of available bandwidth is essential for optimizing network performance and resource allocation. Bandwidth management techniques such as traffic shaping and quality of service help prioritize traffic and allocate bandwidth effectively based on application requirements and network conditions. Okay, so this is what the network administrators do. They make sure that the quality of service is configured in such a way that they prioritize, for example, voice traffic and video traffic over other types of traffic, which may be okay to interrupt those traffic. For example, if you're downloading something from the internet, if you get a blip of a few seconds, that may be okay. But a blip of a few seconds in a voice call or streaming video could be detrimental, right? So if you're having a live voice communication, let's say a conference call or something like that. Okay, great. Thank you for joining. So this is the end of today's lecture. I hope you enjoyed, and I hope you'll join me again. Thank you kindly for your support, and I hope you're enjoying these series of lectures, and I will keep on going to complete this course. So thank you once again. Have a great day. God bless. Take care.